Probably now is the time to discuss our plans for the rest of the semester. And these plans are tentative, meaning if there are people who disagree, please let me know. Well, today is Monday the 11th. So, hello. So the plan is to have classes on December 11th. This is today. On Monday next week, meaning on the 18th, and on Saturday online. Same as we did last week. Then I propose to have an exam on December the 25th. This is Monday again. And then on the next day or the day after, I suggest we have a discussion session, meaning well, for those who get a perfect mark, there is nothing to discuss. But for the rest, I will try to explain mistakes and so on, and this will also be an opportunity to improve the marks, especially and mainly for those who score 3 or less. In other words, this translates as показ работы. We used to have those about 10 years ago. I don't know if they still exist, but anyway, this is an opportunity for people to understand where they went wrong, and as I also said, eventually there will be an option to improve the final mark. Okay, so these are the tentative plans for the rest of the term. Are there any questions?
And at what time on 25th of December the exam will be?
Well, I don't know. I suggest our normal time for 20 p.m.
Because the second year students have a measure theory exam on 16 p.m. the 25th December.
Yes, but there will be some clashes. But are there any second year students in this class?
So it's me, and I also know some who are not attending.
Okay, I will try to. So regarding the exam date, I will try to discuss this with Nina and see if there is a better option. Normally, 2 exams on one day is not ideal. I will try to avoid this. Any more questions? Let's briefly recall what we did on Saturday. Well, we defined the cap. We defined the cap product. And we basically, let me recall the definition. We start with the singular simplex and a cochain, and we apply the cochain to the front face of the simplex, and the result is an element of R. And then we multiply this result by the back face of the simplex, and we get another simplex. And I stated some properties, and I didn't check any of those, but I said that those properties can be checked in a straightforward way. Now. Bless you. Well, the first property, the Leibniz formula. And there's a consequence of this. We get the cup product map on the level of homology and cohomology. Well, there's a couple of properties which say that the cochains of X with the coefficients in R form a module of the chains are a module over the cochains. And again, a consequence homology becomes a module over cohomology. The projection formula if f if f from x to y is a continuous map, then f hash from C lower star and f lower hash from C lower star XR to C lower star YR is a map of C upper star YR modules. For cochains, we have a map in the opposite direction, which makes the chains of X a module over not just over the cochains of Y, not just over the cochains of X, but also over the cochains of Y. And the projection formula says that the natural map f hash is a map of modules. consequence on the level of homology. We have the induced map, and this induced map is a map of H upper star of Y modules. Basically, this is what we did on Saturday, plus the analogs for homology, which are straightforward. Now, the main application of the cap product. The main application of the cap product with the fundamental class gives one of the Poincare isomorphisms. Which one? Well, let's see. Suppose we have M a compact, orientable, manifold without boundary. Orientable means the nth homology of M with coefficients in R is R, where n is the dimension of M. Then there exists an isomorphism from the ith cohomology to n minus ith homology. And this isomorphism is called the Poincare isomorphism. And the Poincare isomorphism is given by phi goes to okay, I think I used mu, so let me stick to this notation. Phi goes to mu cap phi, where mu is an R generator of the nth homology group of M, which we assume to be isomorphic to R. So, in other words, the Poincare isomorphism is given by the cap product with the fundamental clause. Well, before we go any further, let's consider an application. Suppose I have a continuous map from M to N, where M and M are orientable manifolds of the same dimension N and without boundary. Well, as we will see in a minute, there are plenty of maps of this type. Continuous, orientable. Suppose we suppose the manifolds are orientable. So we have Hn M R isomorphic to Hn N R isomorphic to R. Let's choose generators. Or more precisely, R generators. In the same way as we defined the degree a couple of months ago, we define it here as follows. The push forward of mu m is some multiple of mu n, and we just call this multiple the degree. And the statement, which is an application of the Poincare, of the fact that the Poincare isomorphism is given by this formula, is as follows. If D is invertible, in R, then F upper star is injective and the image of F upper star is a direct is a direct summand, which is well, both of those are useful to know. If R is a field, then any subspace is a direct summand, so we don't really get any new information, but this also works if R is Z.
For the upper star is the morphism between cohomology groups of all degrees?
Yes. And as we shall see, we have this this statement for each degree individually. Okay, well, let's prove this. Well, let's look at this diagram. Well, the top arrows, no, the horizontal arrows are the Poincare isomorphisms, and the vertical arrows are the pull back and push forward maps in homology, respectively cohomology, or the other way around. Okay, well, let me, well, I know that these maps are isomorphisms. Let me take a phi inside hn minus 1, hn minus 1, hn minus I of n. And by the way, I've stopped writing the coefficients in R. All coefficients in this diagram are in R. Okay, well, let's see where phi goes under the maps in this diagram. Okay, I take the pullback no, I want to use something else. Okay, so okay, let me calculate the push forward of the Poincare dual of f upper star of phi. So push forward of the Poincare dual of f upper star of phi. Well, what do I get? I get this result by the projection formula. Well, yes, this one is mu m. Thank you. The identity follows from the projection formula. So the result I get is that this diagram does not necessarily commute, but it commutes up to multiplication by an invertible element of R. And the rest is basically simple algebra. I have this map F upper star. And I construct a map G from H n minus I m to H n minus I m, no, n, sorry, such that G composed with F upper star is the identity. How do I construct, there exists a G such that. How do I construct such a G? Well, I go first along this arrow, then along this arrow, then along this arrow, and then I multiply, and then I divide by D. Well, this arrow is an isomorphism, so I can go both ways. And so we have constructed a left inverse of F upper star, which means basically what it says here. F upper star is injective, and the image of F upper star is a direct summand. Okay, so I suggest everyone takes a look at this argument, and meanwhile, I'll go and get some water in the next room. Okay, are there any questions, comments, criticism, protests? Okay, well, to give a more concrete example, let's give a more concrete example. take SG to be an orientable, compact genus G surface without boundary. And suppose we have a map from SG1 to SG2. If the degree of F is not 0, then G1 is greater than or equal G2. For example, there is no map from the torus to the surface of genus 2 of non-zero degree. And we apply this observation by taking R equal Q. Every non-zero element of Q is invertible. So we're able to apply this this argument. Okay, now okay, let me erase everything. Well, let's, just in case, let's define the relative gap product. Well, recall the relative cup product. Again, all coefficients are assumed to be in some ring R, and this works if if the pair A, comma B is excisive, meaning the inclusion of the chain complexes is a quasi-isomorphism. So, what about the relative cap product? Okay, let me put an A here and a B here. Okay, so let's see if I remember the formula correctly. Okay, suppose I have a chain and a cochain. I cap multiply those by the formula we've already seen today and on Saturday. Front face, back face. Okay, well, let's see. Now, suppose I have a chain which is a relative chain. And a cochain which is 0 on every element on every singular simplex that comes from A. Oh, sorry. So, suppose now phi is 0 on all on all singular simplices that come from A. Now, let's consider the map cap phi. This map, what does it do? Well, it takes C of x to C of x. C of A goes to 0 because of this assumption. Well, let's try to think. So what do I need? I need a map from C lower star of x, comma A union B to C lower star of x, comma B. Okay. Okay, so C of A, and I can replace this complex by C of A, C of x, C of A plus C of B. So this is a quasi-isomorphism. Okay, now capping by phi takes chains in A to 0, and it also takes chains in B to chains in B. So, as a result, capping by phi, well, 0 belongs to the chains in B. So as a result, capping by phi takes C lower star A plus C lower star B to C lower star B. Okay, does everyone agree? This thing goes to 0, and this thing goes to itself. So we're left with C C lower star B. So, capping by phi induces a map. I will erase this this diagram because we don't need it anymore. Induces a map C x by C A plus C B to Cx by Cb. This complex is quasi-isomorphic to. I will erase this and then basically write the same thing again. Okay, so we have capping by phi, which is a map from not quite the complex we're after, but almost, meaning the both are quasi-isomorphic. So, on the level of complexes, we have a map C lower star x A plus B tensor C lower star x A to C. C upper star, and here C lower star x, comma B. And what is this? Well, this is by definition the complex C lower star of x by the sum of C lower star of A plus C lower star of B. Well, this thing is by definition a shorter notation for this thing. So we get a formula for the relative cap product. And it's useful sometimes. For example, it will be useful to state the Poincare duality for manifolds with boundary, which we will discuss shortly. Okay, so we do not need this formula at this point, but we will need it in about half an hour. Okay. What next? Well, the next thing I wanted to talk about was the Poincare pairing. So let's talk about the Poincare pairing. Well, the Poincare pairing is non-degenerate. Brilliant. But what is the Poincare pairing? Let's see. So suppose we have M a topological manifold without boundary, compact. Topological manifold without boundary, and let's assume M is R-orientable. Then we have a pairing from H I tensor Hn minus I to R given by phi tensor psi goes to phi cop psi applied to mu m. And another notation we integrate psi cop phi cop psi along m. And if one thinks a little and takes R equal R, the real numbers, then basically we get precisely the same thing here and here.
For the pairing, you need some homology group versus homology not cohomology. H lower star I, not H lower I, of tensor, H upper minus 5.
Okay, we take the cop product, and then we get a cohomology class, and then we evaluate this cohomology class on on the fundamental class. And the pairing is non-degenerate if either R is a field or if R is Z and we replace HI by HI with the torsion quotiented out, and the same for Hn minus I. We quotient it out. If I have an element of the torsion either here or here, the cup product will also be torsion, and so this cup product induces the same pairing for the free modules obtained by quotienting out the torsion. Okay. Well, I suggest we have a break, and then after the break, I'll explain how this follows from the Poincare duality. But before we have the break, I would like to reiterate that we need to take out the torsion. It is not in general true that HI, H upper I, and H upper n minus I are isomorphic. And on Saturday we saw an example where this is not the case. Okay, well, now let's have a break.